slope stability analysis is performed to assess the safe design of a human-made and natural slopes under equilibrium conditions. Slope stability is the resistance of inclined surface to failure by sliding or collapsing. The main objectives of slope stability analysis are finding endangered areas, investigation of potential failure mechanisms, determination of the slope sensitivity to different triggering mechanisms, designing of optimal slopes with regard to safety, reliability and economics, designing possible remedial measures, e.g., barriers and stabilization. Successful design of the slope requires geological information and site characteristics, e.g., properties of soil, rock mass, slope geometry, groundwater conditions, alternation of materials by faulting, joint or discontinuity systems, movements and tension in joints, earthquake activity, etc. The presence of water has a detrimental effect on slope stability. Water pressure acting in the pore spaces, fractures or other discontinuities in the materials that make up the pit slope will reduce the strength of those materials. Choice of correct analysis technique depends on both site conditions and the potential mode of failure, with careful consideration being given to the varying strengths, weaknesses and limitations inherent in each methodology. Before the computer age, stability analysis was performed graphically or by using a handheld calculator. Today engineers have a lot of possibilities to use analysis software, ranges from simple limit equilibrium techniques through to computational limit analysis approaches to complex and sophisticated numerical solutions. The engineer must fully understand limitations of each technique. For example, limit equilibrium is most commonly used in simple solution method, but it can become inadequate if the slope fails by complex mechanisms. In these cases, more sophisticated numerical modeling techniques should be utilized. Also, even for very simple slopes, the results obtained with typical limit equilibrium methods currently in use may differ considerably. In addition, the use of the risk assessment concept is increasing today. Risk assessment is concerned with both the consequence of slope failure and the probability of failure. Within the last decade, slope stability radar has been developed to remotely scan a rock slope to monitor the spatial deformation of the face. Small movements of a rough wall can be detected with sub-millimeter accuracy by using interferometry techniques. Limit analysis. A more rigorous approach to slope stability analysis is limit analysis. Unlike limit equilibrium analysis, which makes ad hoc though often reasonable assumptions, limit analysis is based on rigorous plasticity theory. This enables, among other things, the computation of upper and lower bounds on the true factor of safety. Programs based on limit analysis include Optim2 general-purpose software for geotechnical applications, including slope stability, limit state, general-purpose geotechnical software application based on discontinuity layout optimization for plane strain problems including slope stability. GEO5 slope stability program is used to perform slope stability analysis of embankments, earth cuts, anchored retaining structures and MSE walls. Stereographic and kinematic analysis. Kinematic analysis examines which modes of failure can possibly occur in the rock mass. Analysis requires the detailed evaluation of rock mass structure and the geometry of existing discontinuities contributing to block instability. Stereographic representation of the planes and lines is used. Stereonets are useful for analyzing discontinuous rock blocks. Program DIPS allows for visualization structural data using stereonets, determination of the kinematic feasibility of rock mass and statistical analysis of the discontinuity properties. Rockfall Simulators. Rock slope stability analysis may design protective measures near or around structures endangered by the falling blocks. Rockfall simulators determine travel paths and trajectories of unstable blocks separated from a rock slope face. Analytical solution method described by Hung and Amp. Evans assumes rock block as a point with mass and velocity moving on a ballistic trajectory with regard to potential contact with slope surface. Calculation requires two restitution coefficients that depend on fragment shape, slope surface roughness, momentum and deformational properties, and on the chance of certain conditions in a given impact. Program ROCFALL provides a statistical analysis of trajectory of falling blocks. Method rely on velocity changes as a rock blocks roll, slide or bounce on various materials. Energy, velocity, bounce height and location of rock endpoints are determined and may be analyzed statistically. The program can assist in determining remedial measures by computing kinetic energy and location of impact on a barrier. This can help determine their capacity, size and location of barriers. Numerical methods of analysis. Numerical modeling techniques provide an approximate solution to problems which otherwise cannot be solved by conventional methods, e.g., complex geometry, material anisotropy, nonlinear behavior, in situ stresses. Numerical analysis allows for material deformation and failure, modeling of pore pressures, creep deformation, dynamic loading, assessing effects of parameter variations, etc. However, numerical modeling is restricted by some limitations. For example, input parameters are not usually measured and availability of these data is generally poor. Analysis must be executed by well-trained user with good modeling practice. User also should be aware of boundary effects, meshing errors, hardware memory and time restrictions. Numerical methods used for slope stability analysis can be divided into three main groups: continuum, discontinuum in hybrid modeling. Continuum modeling. Modeling of the continuum is suitable for the analysis of soil slopes, mass of intact rock or heavily jointed rock masses. This approach includes the finite difference and finite element methods that discretize the whole mass to finite number of elements with the help of generated mesh. In finite difference method, differential equilibrium equations are solved. Finite element method uses the approximations to the connectivity of elements, continuity of displacements and stresses between elements. Most of numerical codes allows modeling of discrete fractures, e.g., bedding planes, faults. Several constitutive models are usually available, e.g., elasticity, elastoplasticity, strain softening, elastoviscoplasticity, etc. Discontinuum modeling. Discontinuum approach is useful for rock slopes controlled by discontinuity behavior. Rock mass is considered as an aggregation of distinct, interacting blocks subjected to external loads and assumed to undergo motion with time. This methodology is collectively called the discrete element method. Discontinuum modeling allows for sliding between the blocks or particles. The DEM is based on solution of dynamic equation of equilibrium for each block repeatedly until the boundary conditions and laws of contact and motion are satisfied. Discontinuum modeling belongs to the most commonly applied numerical approach to rock slope analysis, and following variations of the DEM exist. Distinct element method. Discontinuous deformation analysis, particle flow codes. The distinct element approach describes mechanical behavior of both the discontinuities and the solid material. This methodology is based on a force displacement law and a law of motion. Joints are treated as boundary conditions. Deformable blocks are discretized into internal constant strain elements. Discontinuum program UDEC is suitable for high-jointed rock slopes subjected to static or dynamic loading. Two-dimensional analysis of translational failure mechanism allows for simulating large displacements, modeling deformation and material yielding. Three-dimensional discontinuum code 3DEC contains modeling of multiple intersecting discontinuities, and therefore it is suitable for analysis of wedge instabilities or influence of rock support. In discontinuous deformation analysis, displacements are unknowns and equilibrium equations are then solved analogous to finite element method. Each unit of finite element type mesh represents an isolated block bounded by discontinuities. Advantage of this methodology is possibility to model large deformations, rigid body movements, coupling or failure states between rock blocks. Discontinuous rock mass can be modeled with the help of distinct element methodology in the form of particle flow code, e.g. program PFC2D, 3D. Spherical particles interact through frictional sliding contacts. Simulation of joint-bounded blocks may be realized through specified bond strengths. Law of motion is repeatedly applied to each particle and force displacement law to each contact. Particle flow methodology enables modeling of granular flow, fracture of intact rock, transitional block movements, dynamic response to blasting or seismicity, deformation between particles caused by shear or tensile forces. These codes also allow to model subsequent failure processes of rock slope, e.g. simulation of rock hybrid, coupled modeling. Hybrid codes involve the coupling of various methodologies to maximize the key advantages, e.g. limit equilibrium analysis combined with finite element groundwater flow and stress analysis adopted in the SVOFFICE or GeoStudio suites of software. Coupled particle flow and finite difference analyses used in PF3D and FLAC3D. Hybrid techniques allows investigation of piping slope failures and the influence of high groundwater pressures on the failure of weak rock slope. Coupled finite distinct element codes, e.g. ELFIN, provide for the modeling of both intact rock behavior and the development and behavior of fractures. Rock mass classification. Various rock mass classification systems exist for the design of slopes and to assess the stability of slopes. The systems are based on empirical relations between rock mass parameters and various slope parameters such as height and slope dip. Bibliography.